effect in the Mott insulators. So Rodrigo, please.
So hi everyone. First, I'd like to thank the organizers for putting together this nice workshop and inviting me. It's really fun to see so many friends together. And basically, this is going to be a story about a Kondo effect in quantum spin liquids. I'm going to start setting up the stage by discussing the effects of magnetic impurities and what I mean by this spinon-Kondo effect. And the model we actually used or studied is in one dimension. So I'm going to study a Mott insulating Hubbard's chain with a magnetic impurity. And we're going to look for signatures of the spinons in the electron density of states. So the idea is that doing tunneling at the boundary of a Mott insulating chain can give you more direct probes of spinon excitations than if you do similar experiments in the bulk. And then I'm going to show you some numerical results at the end. And this is work done in collaboration with Bruno Marquez and Karen Hallberg in Argentina, Reinhold Eggert in Germany, and Tim Bauer was a student with Reinhold, and he's now a postdoc in Tokyo. Okay, so before I move on to Mott insulators, let me remind you about some features of the Kondo effect, the usual Kondo effect in metals, so we can compare later with what happens in Mott insulators. So we can think about the Kondo effect as this renormalization of the exchange interaction between localized spins and the itinerant electrons that happens due to this spin flip scattering. And that has manifestations in many different physical properties. In the original version of the problem, as people were interested in understanding the resistivity at low temperatures, and within perturbation theory, resistivity comes from second-order perturbation theory. If you go to higher orders, you start to see that the conductivity increases as you go to lower temperature, and you can cast the result in terms of a renormalization of the effective coupling constant that actually diverges as you go to lower energies. By analyzing when this kind of expression for the effective exchange coupling breaks down, you can extract this natural energy scale, which is the Kondo temperature. It's non-perturbatively in this coupling JK. And if you go to lower energies below this Kondo temperature, you have to understand this strong coupling fixed point. And the simple picture is that at that fixed point, you have some infinite exchange coupling, and then the impurity spin will be screened by the conduction electrons. That can be discussed in terms of an effective pi-over phase shift in the language of scattering for the conduction electrons, which is like a change in the boundary conditions, which again can have many different consequences for physical properties. And finally, there is also this the famous Kondo resonance, which is a very important paradigm of how we think about quantum many-body phenomena. It's even on the cover of Hilson's famous book on the Kondo problem. And the idea is that if you measure the local density of states for the conduction electrons, you get this very narrow peak at the Fermi level, which can be observed in the STM experiments by the differential conductance, and the width of this peak in the zero temperature limit is essentially the Kondo temperature. So the game now is you can look at some of these keywords that I've highlighted and ask how many of these will survive if I trade my metal for a Mott insulator, then does this even make any sense? And particularly, we're going to talk about whether there is some version of the Kondo resonance that could be observed in a Mott insulator, and what can we learn in that case. So by Mott insulator here actually means a phase that will have a charge gap but no magnetic order, so namely a quantum spin liquid of some particular kind that I'm going to specify now. So the idea is that magnetic impurities in spin liquids have been discussed for some time, and you can discuss or describe a spin liquid in terms of the fractionalization of the electron, in terms of excitations that will carry charge. These are sometimes called chargons or holons, depending on the context, and spinons that will carry the spin but no charge. And in some cases, you want to gap the charge, so you have a Mott insulator, but in some cases, the spinons can be gapless and can form what is called a spinon-Fermi surface. And one way to describe this theoretically is by means of these Python constructions that come in many flavors. One example is this slave rotor formalism, where you write down the electron operator in this way. This F would be a spinon, a fermionic spinon, and theta here is a phase field which is conjugated to the total charge. You can actually write this exponential of the phase here as some X operator, which can be treated as a boson in some approximations. But if you plug this kind of representation into the Kondo coupling, you get something like this. And what you see here is that the Kondo coupling will actually, it looks a lot like what we had before, but now it only involves the fermions that represent the spinons that carry no charge, but just the spin. But other than that, it's a coupling between a localized moment and some kind of fermions in this description. So which already suggests that the Kondo effect will survive in this language if you replace the electrons by fermionic spinons with a spinon-Fermi surface. This picture is a bit too simple because this kind of representation comes with a U1 gauge structure. The physical electron operator is invariant under this U1 phase transformation, which in theory means that actually there is an emergent gauge field that will generate interactions between your bosonic holons and your fermionic spinons in this kind of theory. And this is an inherently strongly coupled theory, so the best you can do is to treat it with some mean field approximation or a large n. And in that approximation, the conclusion is that actually this gauge field does not do much in terms of physical properties that are important from the Kondo effect. Basically, we recover some kind of Fermi liquid behavior for the strong coupling fixed point, with this difference that what is screening the magnetic impurity are the spinons rather than the electrons. So this idea has been tested experimentally by trying to measure the contribution of impurities to magnetic susceptibility. Some things agree with the theoretical prediction of a Fermi liquid behavior, some don't. And then when it doesn't, you blame it on the interactions mediated by the gauge field, right? So it's kind of a complicated story here. I'm thinking of one specific, which I forgot to cite here, but they had some sub 2D material. It was a Kagome lattice that they proposed was a quantum spin-on Fermi surface state, and they did μSR, so they measured the night shift and saw that it saturates at low temperatures. And you see saturation at low temperatures. But then there are some weird power laws that in some field dependence that they don't understand. And then this topic had a revival a few years ago because now one can have local probes of this kind of spinon-Kondo effect. So these were experiments done in this, it's a 2D material where the unit cell, you have this kind of Star of David unit cell with a charge density wave on top of a triangular lattice, and you have a spin 1/2 per unit cell. So it's essentially a triangular lattice of stars of David. And then there are theoretical predictions that the effective spin model for this material could give a quantum spin liquid ground state with a spinon-Fermi surface. So people did this experiment by placing a single cobalt atom on top of the tantalum here, on center, and then comparing with the density of states that is measured far from the cobalt impurity. And then far from the impurity, what you see here, this is tunneling into the Mott insulator. You see that the IDV vanishes unless the bias voltage reaches some finite values, which is like the edges of this upper and lower Hubbard bands. But if you do this on top of the magnetic impurity, you see some extra peaks, which were interpreted as evidence of something that comes from the interaction, some kind of bound state that is induced by the presence of this magnetic impurity interacting with this quantum spin liquid. And there are similar observations in another 2D material, in this case here. So, oops. And then the theory behind this experiment was explained in more detail in this paper. And what they did was you want to describe tunneling into the insulator, so you start with some kind of modified Anderson model. So you have a Hubbard U both at the impurity side and in the bulk. So you want to open up the Mott gap in the bulk. And then you use this kind of slave rotor representation to calculate the local density of states. The electronic density of states comes from a convolution between the charge-on or hole-on density of states and the spin-on one. And then you can compute the density of states. So this is like the charge part, this is the spin-on part. You take some convolution of both, and you treat this model within this slave rotor mean field theory. But that is not enough. They show that if you want to get from the theory this bound state or sub-gap peak, you also need to add interactions between holons and spin-ons, which are treated with some RPA approximation. And only when this interaction is strong enough do you get this peak that splits out from the continuum and appears here. Right? So that was the theoretical proposal that how to explain this. And basically it requires two things. It's important that you have a Kondo resonance in the spin sector in terms of the spin-on spectral function to enhance the density of states at low energies, but also you need this very strong spin charge interaction, which is beyond usual mean field approximations. So what we wanted to do here is to ask if there is a simpler version of this problem in one dimension. Well, the first reason is that we didn't know if this was possible in 1D. I couldn't find the answer anywhere, so I thought maybe we should figure this out. But a few reasons to look into this problem is that, first of all, spin charge separation is very well established in 1D. It's a hallmark of Luttinger liquids, and then what you have to do is gap out the charge sector to get the Mott insulator. Also, there is Kondo effect in Heisenberg spin chains. In a very strict sense, if you only take the spin model and you couple a magnetic impurity at the boundary of a Heisenberg spin chain, you get a renormalization of this Kondo coupling, which is exactly the same as the renormalization with conduction electrons. And this is, again, because of spin charge separation. All the action happens in the spin sector, right? And people can even extract Kondo temperatures from this spin problem and as a function of this coupling. And you observe scaling functions and everything. Also, there has been some renewed interest in this problem, work by Nathan and Ray, that discussed some regimes where you can get bound states in the spin chains if the Kondo coupling is strong enough. We wanted to understand if there is any relation with the spinon-Kondo effect that I was talking about before. And finally, oops, wow, that was... Sorry. And finally, there have been some very interesting experiments recently, new versions of spin chains where you can do tunneling experiments. These are so-called nanographene spin chains, where you put together these clusters of carbon atoms, and depending on the form and the shape of the cluster, you can get a spin 1/2 per unit cell. And this is the tunneling response for chains of different lengths of order 10 here as a function of energy. I think it's very cool that you can, comparing theory and experiment, I think it's very cool that you can even see the difference between the spectrum of even and odd chains. Like for odd chains, you get the ground state is a doublet, and you get a peak at zero bias peak, right? So, these are for uniform chains with open boundary conditions, but the experimentalists tell us that they're now moving to look at impurity problems as well. So it's maybe some Kondo problem in this case. So here is the model that we analyze. Is some kind of a Anderson model in 1D, where I add, so there's hopping in the bulk, and this hopping to the impurity side at the boundary, and there is a UD at the impurity side and U in the bulk. And then when you take the infinite chain, this is just the Hubbard chain. It's exactly solvable by beta-ansatz. We know the exact expression for the charge gap. Another important scale that we're adding here is UD at the impurity site. And I'm going to work in this regime where UD is actually smaller than the Hubbard U in the bulk. I'm going to focus on this regime because that's the regime where you found something. I don't want to say that there is nothing in the other regime because we didn't do an extensive search, right? But I think it's harder in the other regime, but I won't go into the details. Okay, and this is the opposite than you usually have in the Anderson model. And then we measure the local density of states near the boundary, in particular the impurity site, J equals 0, or the first site at the boundary of the chain, J equals 1. So we can approach this problem coming from the weak coupling regime, very small U using bosonization, which gives you the spin charge separation. Here, the Hamiltonian is written, Hamiltonian density in terms of this non-abelian bosonization. So these are currents, vector current operators. Essentially, the Z component of this vector is proportional to the derivative of a bosonic field. And these bosonic fields describe the collective charge and spin modes in the 1D system that propagate either to the right or to the left. They're not independent because of open boundary conditions, so you have to glue them here at the boundary. But essentially, from this part, you get a free bosonic theory in one dimension, and this is the part that contains the interaction. And then you have to ask what is coupling constant here in the charge and spin sector do. In the charge sector, this interaction is actually marginally relevant. This will open a Mott gap, which is exponentially small at weak coupling. In the spin sector, it's irrelevant. Then you get gapless spin excitations, like in the Heisenberg chain. And these are described by some conformal field theory, which is the Weissman-Witten model. It's essentially a Luttinger liquid with SU2 symmetry. And I also want to emphasize that we know the operator content of this theory, and in addition to this current operators here, we also have spin 1/2 operators, the spin 1/2 primary field, which forms this doublet. This transforms as a spin 1/2 representation of SU2, and these operators, written as in terms of vertex operators, exponentials of the bosonic field, they carry a spin 1/2. These are the operators that are actually identified with the spin-on later on. Okay, so now, that was coming from weak coupling, but then you can crank up your Hubbard U and increase the Mott gap. The picture doesn't change much in the sense that you still have a gap in the charge sector and gapless spin excitations. But then we also want to describe the charge excitations in this regime. Actually, at large U, it's convenient that you get this kind of Ogata-Shiba separation of the wave function in terms of spin and charge. You can describe the holons or doublons in terms of spinor fermions. So I can describe this as some kind of particles that move and form some effective bands, which are gapped. And we basically adapted some previous work where we described charge dynamics of finite energy. For this, you have to go a little one step beyond the usual Luttinger model because you have to add these gapped charge excitations. But then you can do this in terms of some effective mobile impurity models. And then it looks like this. So I have this D operator that describes my holon or doublon. And then the gapless spin excitations are bosonized. And then if you go through this framework, you can rewrite the electron operators in terms of creating a holon, which is like this mobile impurity, and this spin-on operator, the vertex operator that I mentioned before. And here it's important that the spin-on here in this theory is not a fermion. It is actually a semyon in the sense that it has scaling dimension 1/4, which controls the statistical phase. So in 1D, I cannot do this, like carry one particle around each other, like the way you do in gapped phases in 2 dimensions, but you can still define a statistical phase in this sense in terms of changing the order of the operators along the line. And here you pick up this phase, which is pi/2, then it's a semyon. Okay, so it's not a fermion. And then this is the theory for the bulk, and then without the magnetic impurity, we can use this theory to predict that the the density of states near the boundary will vanish as you approach the Mott gap from above. It will vanish linearly. Now we can bring back our magnetic impurity. We can start again at weak coupling in this regime here. So I actually will consider U is much smaller than U. It's convenient for approximations. And if you integrate out charge fluctuations, basically from second order perturbation theory in this hybridization T prime, you get this kind of Hamiltonian where you still have the gapless spin modes in the bulk. This here accounts for some energy cost for changing the number of electrons at the impurity site, which is this energy cost of order UD over 2. And this is essentially the Kondo coupling that I just rewrote in terms of a longitudinal term and a transverse term that contains the spin flip terms. So if you forget about this term for a minute, this here just describes some coupling of the spin density of the spinons near the boundary of this chain to this magnetization at the impurity site. So this is pretty much like the Fermi edge singularity, but in terms of spin operators. And this model is actually exactly solvable by some unitary transformation. And what you get is some power loss singularity at the threshold for creating this excitation. And in general, the exponent here that you see for the local density of states would depend on this coupling constant lambda parallel here. So, which here I have rewritten in the usual language of Fermi edge singularity. This is related to the phase shift for scattering of this effective potential, which is small in the weak coupling limit. But of course, you cannot neglect this. Is an important part of the Kondo effect. These are the spin flip processes that we normalize the Kondo interaction. And once again, if you stay in the sector where you have one electron at the impurity site, this is very much like the usual Kondo problem, the same kind of RG equations. This coupling will flow to strong coupling. And then the question is, what do you get at strong coupling? So I want to argue that actually if you flow to strong coupling, you get the largest possible of this scattering phase shift, which is pi over 2. We can actually argue that by looking at the boundary magnetization, which is written in bosonization form in terms of this way, and if you think that in the strong coupling limit, you should get a Kondo singlet, you can show that this phase shift really has to be pi over 2. And if you set the value of the phase shift in the power law that I showed before, this would imply that here you actually get a square root singularity at this threshold, which is below the gap, if UD is less than U, which is universal. This exponent would be controlled by the Kondo effect that takes you to that universal value of the phase shift, as long as you can probe the local density of states close enough to the threshold, right? So this is strong coupling behavior. You have to be at some energy scale below the Kondo temperature, which means the energy has to be close enough to the threshold like this. Another argument here is that you can look directly for some simple picture for this strong coupling limit. Again, if I go to there are two strong coupling limits, really, like large Kondo coupling and large U. If I go to large U, I can describe holons as spinless fermions hopping on the lattice and then include the impurity site. And in this regime, what you see is that the Hubbard U is some kind of effective chemical potential for the holon, right? The energy cost for occupying different sites. And when UD is much smaller than U, this holon is actually attracted to the impurity site, and you get a bound state there. So you can then picture what's happening in this tunneling process when you try to inject the electron. If you fractionalize, it becomes a holon and a spinon. This holon will actually occupy the bound state, which only sets the energy of this threshold. And then when you do this, you actually break the Kondo singlet when you occupy in this boundary state, the impurity site. And then you have to send the spinon back to the chain at the boundary. And this is again this is spin-on operator here. And here again, it's important that this is not a fermion. It has an operator with scaling dimension 1/4. And you can compute correlation functions to see how the correlation function decays in time, do some Fourier transform, and you realize that in frequency space, that's actually the square root, a simple way to understand the square root singularity near the threshold in the frequency domain. Right? And it's also important that this operator here by itself is non-local, the single spin-on operator, so you cannot see it in a Heisenberg spin chain by probing the spin spectrum, but here it's possible because it's actually combined with something that acts in the charge sector but only adds a hole onto this bound state. Right? So all the more interesting dynamics will come from the spin-on, so you could basically probe in the spin-on the properties of this operator that creates the spin. So here is the cartoon picture for what I just told you. I want to contrast the usual Kondo resonance with the singularity that we're talking about here. So you can think that like this. Say you start with a metal and some like in the Anderson model with some impurity levels, which are initially decoupled from the metal. If you turn on the hybridization, this coupling between the impurity and the conduction electrons, the sharp feature is the Kondo resonance with TK at the Fermi level. But let's say instead of doing this, let's do this one first. I turn on U, a very large U in the bulk. Then I open up the Mott gap, and my impurity levels are now inside the Mott gap. If now I turn on this hybridization coupling with the impurity, what you get is this threshold singularity, where the exponent here is 1/2, and it's actually controlled by this spinon-Kondo effect. And that's my simple cartoon picture that comes out of these calculations. Of course, the question is, if I try to look for signatures of this behavior for a finite chain, so which is not in the thermodynamic limit, also if you have some finite energy resolution, if you try to do this in experiments with nanographene chains, for example, what can you see? And this is where we did some numerics. So this is basically DMRG for chains of 23 sites in the bulk plus the impurity site for this choice of parameters with UD less than U. And also in this DMRG method, you have to set some broadening. So it seems a finite system. You have to set some broadening of the peaks by hand. This Lorentzian broadening, which is of order 1/L. Oops. And here this is a problem because to see the square root singularity I was talking about before, you need to be close enough to the threshold, but also this could be a problem because if you're at weak coupling, then the Kondo temperature is going to be very small, right? It's exponentially small at weak coupling, so you have to be very good energy resolution. Also, if the Kondo temperature is very small, the size of the Kondo cloud is very large. It could be larger than my system size, and then you don't see the strong coupling limit either for this reason. Right? So this is the reason why we actually, numerically, we look at larger values of T prime. So starting with this T prime of 0.6, and then even higher values to move towards this strong coupling fixed point. Right, and then here I'm showing the result for this value of T prime at different sites as a function of energy. This here is the Mott gap. Anything you see here has to do with the presence of this magnetic impurity site at the boundary. Right, so this peak is strongest, of course, at the impurity site. We checked that this is a bound state because, as you could see in the previous plot, the weight of this subgap peak decreases with the distance from the boundary. You can just integrate the local density of states and see that it decays exponentially. So it's really related to a bound state. And we also wanted to see if we could try to extract from this data with finite energy resolution the exponent that I was talking about. And then here I'm showing the result for T prime equals 1.8. You can see that already this peak is very asymmetric, so this is not a Lorentzian. It could be some kind of power law exponent here. And to extract the exponent, we compare the numerical results with some a broadened version of the power law singularity. It's basically a convolution of the power law with the Lorentzian with the width that we know. So you can extract the value of the threshold and the exponent by fitting this near threshold behavior, and the result is here. So you see that if T prime is small, we basically measure some exponent close to 1, which is like what you expect for a Lorentzian, but this value of the exponent decreases and approaches 1/2 as you move towards the strong coupling limit. So to conclude, the main message here is that you can use a scanning internally spectroscopy to measure many different interesting excitations of magnetic systems in Mott insulators, even beyond the example that I discussed here. So I wanted to mention that similar ideas have been used to propose local probes of Majorana fermions in Kitaev spin liquids. William Natori has a very nice paper about this. Recently, with Eric, we also looked at Magnon bound states in polarized phase of Kitaev-Heisenberg models. And in the specific problem that I told you about, what it shows is that this spinon-Kondo effect happens in one dimension, and the main signature is this power law singularity with below the Mott gap, where the exponent is controlled by the Kondo effect. And maybe this is my last remark, more on the more speculative side. Maybe there are some lessons for the higher dimensional case, because maybe it's interesting to look at this regime of UD less than U also in 2 dimensions to probe the spinon in the 2D spinon Fermi surface state beyond Python mean field approximations, right? It's actually known that if you take into account the gauge field fluctuations beyond these approximations, the theory is strongly coupled. You actually don't have well-defined fermionic quasi-particles is an example of a non-Fermi liquid state. So maybe there is something similar to probing anomalous dimensions of fermi, this kind of spinon excitations in higher dimensions. And with that, I'll stop here, and thank you for your attention.
Okay, I have time for your questions.
Rodrigo, how important it is to have just the impurity on one side? Like if I had also put another impurity mirroring it on the other side, the effect goes away? Or
if they're very far apart?
Yeah, so that's the question. Is there like a critical distance beyond which?
So this is like a bound state, right? So you can see, yeah, you can probe the vicinity of the boundary, and the effect will decay as you go into the bulk. So it's okay if you have an impurity on the other side as well. Sometimes when people do simulations for finite size systems, it's actually inconvenient to add, like we started an even a chain with an even number of sides, and you want L to be even, so you add 2, knowing that it's actually, if the chain is large enough, they'll be completely decoupled, right? So so that's okay.
More questions?
So do you have any expectations for the case of UD greater than U? Then
yes.
The impurity states will fall inside.
That's right. Yeah. So if you that's actually important in the 2D problem, because I forget if I mentioned this. In their case, it was UD greater than U. So there's nothing below the gap to begin with, right? So you had to form the bound state from some very strong interaction, so something will come down below the gap, right? So if that happens here, we haven't seen anything like that numerically, but if it happens here in some regime, then you also have to do with forming the bound state from very strong interactions between spinons and holons. In 1D, with this geometry, I think it's unlikely, because in my mind, the picture is that you would need some forming a bound state depends on the density of states near this threshold, right? So, and like I said, in 1D, the density of states will vanish linearly at the threshold. So it's not going to form very easily. That's different from the 2D case where the density of states are finite to begin with. So you need very strong interactions. Maybe it's unlikely that it happens.
But even in 1D, you expect to form some singularity like you have here inside the gap?
In the other case, yeah. So in general, if you bring some, if you have a peak, something below the gap, and you couple this, it's like this level to the gapless modes in the spin sector. In general, I would expect a power law singularity of some kind. Yeah.
Okay, thank you.
Yeah, I actually have a follow-up question. So you could, in principle, plot, like in the 2D case that you showed, you could, in principle, plot the spectral density on the spinel sector and the charge sector separately.
Yes, yes.
And then in the spinel, there will be a resonance.
Yes.
And is TK related to the width of that resonance in the spinel sector?
Exactly, yes.
Okay, I see.
So it's very much like the electron problem. So with the...
More questions? Yeah, okay.
So just a question to sort of educate myself. This might be a very dumb question, but so in the Howard model, just in the normal Howard model, when you gap the charge, the spinon is supposed to be a semyon?
Yeah, in the sense that I described here,
Yeah.
right? It's a gapless phase. So in the sense that you look at the phase that you get from exchanging the operators along the line. That's,
right. So I imagine that in that case, the Howard model will be just kind of the same as a Heisenberg antiferromagnet. Is the Heisenberg
in the low, yes. In the low energy sector, if you forget about charge excitations, that's the effective theory.
And it will
so
be
it's
a
like a
semyon
Heisenberg
for
chain.
the Heisenberg antiferromagnet.
Yes.
So if you have if you go like X, Y eventually, then the statistics will change, right? This angle will change if I don't have SU2.
Yes, that's right. So the spinon here, actually that vertex operator, it has that scaling dimension because of SU2 symmetry.
Yeah.
More generally, it could be like a Luttinger liquid where the
Right.
scaling dimension changes continuously with the interaction parameters.
Right, so if you break SU2, then is it
could
crucial
be-
that it's a semyon to form this bound state? Or
No, but then I would lose some degree of universality in terms of scaling dimensions of operators. You could still get power law singularities, but the exponents would depend on these more general scaling dimensions.
Okay, thanks.
Thank you.
Okay, any more questions? So if not, let's thank Rodrigo and all the speakers in this session. Mr. Chairman, are there announcements?